What we're looking at today is segment lengths. So we're actually looking at the length of segments. Up to now, we've been looking at degrees and arc measures and angles. Now we're actually going to look at lengths of chords and their measures. If two chords intersect in the interior of a circle, then the product of their lengths of the segments of one chord is equal to the product of the lengths of the segments of the other chords. So we'll multiply their two segments together. So we're going to be multiplying AE and EB by EC and DE. So the two parts will multiply them together of each line, and they would be equal. So when we look at this here, and this does look a little bit harder than what it actually is going to be, is we're going to multiply the segments together. So for our chord ML, one of its segments is x plus 2. The other part of the segment is x plus 1. So for ML, the two segments are x plus 2 and x plus 1, and we will multiply those two together. Now the other line, the other chord, KJ, one of its segments is x, and the other segment is x plus 4. So the product of the two parts of each chord, the two segments of each chord, multiplied together will be equal to each other. Any questions on how we set this up? Okay, now we need to use our distributive property. We can multiply through. So the first thing we can do is we can distribute through with x. So x times x would be x squared. X times 1 is going to be plus x. And then we can distribute through with the 2. So we do 2 times x is going to be plus 2x, and 2 times 1 is going to be plus 2. So this is going back to algebra when we use our distributive property to multiply through each one here. Now we can do the same thing with our other term, other side. We can distribute the x. So our x times x would give us x squared, and x times 4 would be plus 4x. I can. Any questions on any of this here? Any questions on how we got any of these terms? So we distributed through, we multiplied through. Our x times x does give us x squared. Our x times 1 gave us x. 2 times x gave us our 2x, and 2 times 1 gave us 2. And then we multiplied through the other side. Our x times x gave us x squared, and our x times 4 gave us 4x. Now what we can do at this point is we can combine like terms. Anything that are like terms, we can put them together. So here, where our x and 2x are the only like terms on either side, so we can combine those. We'd have x squared plus, well, x plus 2x gives us 3x plus 2 is equal to x squared plus 4x. Now, because we do have higher degree polynomials, we have x squared, we have x to a power greater than 1, we want to get those on the same side. So what I'm going to do is I'm going to move this x squared over to the other side by subtracting x squared from both sides. And it works out that both of these will cancel out completely. Which is kind of convenient for this here, because x squared minus x squared is 0, which leaves us with 3x plus 2 is equal to, well, x squared minus x squared is, just leaves us with our 4x. So we have 3x plus 2 is equal to 4x. Exactly, we can subtract 3x from both sides to get x by itself. Four x minus 3x would give us, so the value of x that we are looking for is 2. So it worked out here quite nicely that all the variables essentially simplified down, and we didn't have to do much in solving. Are there any questions on this here or any of the steps?
Does it matter which one is it? On the figure, does it matter where, like you put x plus 2 and x plus 1 together, could it have been, like, does it matter where you put? Yep.
Could we have done x plus 1 times x plus 2? Yeah.
And then it just has to be the bigger one.
So here, it's part of the line. Since x plus 1 and x plus 2 are part of the line, the chord ML, they go together. Since x and x plus 4 are part of the line JK, those go together. Now, the order in which we place them really doesn't matter, because when we use multiplication, 4 times 2 is the same as 2 times 4. We can do it in any order. So we could have had x plus 1 times x plus 2, or as we have it here. But we cannot switch out x plus 1 and x, because they're part of different chords. So, I mean, we could have had like this here. Yeah, because it is equal. There is equality here. So how we place them doesn't matter, because A is equal to B, B is equal to A. We can switch it. Yes. Because what was it asking for? ML and JK, so we needed to find the value of x. Well, we did that, and we found out that x is 2. So 2 plus 2 gives us 4. 2 plus 1 is 3. This is 2, and 4 plus 2 is, so KJ or JK would be 2 plus 6, which is, now the other segment is ML. Well, part of M is 4, the other part is 3. 4 and 3 is, and that would be it. Those would be our lengths. Any questions on this here? Okay. We have another one like it here. Find A, B, and PQ. So just like on the last one we did, we're going to find the value of x so that we can plug it back in to find the lengths of the lines. So how can we set this equation up? Yes. X plus 6 times x. And then we're going to distribute. So our x times x would be x squared. X times 4 is going to be plus. And that takes care of the first x. Now we can do the same thing with our 1. 1 times x would be plus, and 1 times 4 is plus. Now, it doesn't matter which way we do it for the second one, because we can multiply x and then 6 to x, or we can do it the other way around. We will still get the same thing, because x times x would be x squared. X times 6 is going to be plus. Any questions on any of the steps we've done so far? Now we can combine like terms, which would be x squared plus 5x plus 4 is equal to x squared plus We can subtract x squared from both sides, because x squared minus x squared will, and well, x squared minus x squared will cancel out, leaving us with 5x plus 4, bless you, is equal to 6x. Yes, then we would subtract 5x from both sides. Which tells us x is equal to 4. Any questions on any of this here? Now, these here have worked out quite nicely so that pretty much everything simplifies down cleanly and nicely, and we get these nice whole numbers. Now, at this point here, we do need to come back to the top and plug it in. So are there any questions on how we solved anything before we plug it back in? Okay. So when we plug this back in, we're plugging in the value of x. Well, here, x is just going to be 4. Well, 4 plus 6 is? This length 4 plus 4 is? And 4 plus 1 is? So PQ, its length is going to be these two added together. 5 plus 8 gives us?
How did you get the numbers?
So for any of these numbers here, so we know x is equal to 4, yes? So for this part here, I just have x as 4. So for the other part, we have x plus 6. So we would have 4 plus 6 would give us 10. So here we'd have 4 plus 4, which would be 8, and 4 plus 1 would give us 5. I went on and just did that and not wrote it out. But I thought, or kind of, it seemed, my assumption was y'all were comfortable with that. If you need me to write something out, just go on and ask. Or if something doesn't make sense, ask. Especially with me jumping steps on these last few here. Because with A to B, one section's 10, the other section's 4. So we can add those together and get 14. Any questions on any of this here? And the theorem really does hold true, because if we wanted to look at it, 5 times 8, what is 5 times 8? 40. The other sections would be 4 times 10, which is 40. The product of the two segments do equal each other. Questions on any of this here? Let's do another one that's a little bit nicer than the ones we've been doing. Because again, if we have two chords that intersect inside the circle, then their product of their two segments will be equal. So for us here, how would we set that up? So, yes. 6 times 4, yes. So it's not always going to be that we have to have it as x plus 1 and x plus 2 and all this stuff set out here, because we can just have numbers like they give us here. Well, 3 times x, or x times 3, is going to be 3x. 6 times 4 is, and then we would x is equal to 8. And it just wanted us to find the value of x. Because even if we wanted to plug it back in, well, that would just be 8. So one segment would be 11, and the other segment would be 10, because we can just add those numbers together. Any questions on any of this here? Find the value of x. floor. What can we do first? Okay. Exactly, it would be 2x plus 2 because we can distribute the 2. 2 times x would be 2x, and 2 times 1 is 2. And now what? Subtract 2 from both sides. These would cancel, leaving us with 2x is equal to. Divide both sides by 2. And it just told us to find the value of x, so we're not worried about finding any lengths. Any other questions on this here before we move on to the next theorem with circles that we're going to look at today? Okay. So we have two other theorems that we're going to look at dealing with tangent segments and secant segments. So a tangent segment is a tangent line that goes from the point of tangency to the line outside the circle, to a point outside the circle. And our secant segment goes through the circle and connects to a point outside of the circle. Now we can either have two secant segments that we're going to look at, or a segment or a secant segment and a tangent segment. So we're either going to have two secant segments or a tangent and a secant, one of each or two secants. Now the secant lines are broken up into two parts. We have the external part that's outside the circle, and we have the internal. And the external and internal actually do have a correspondence, a relationship of how they work. And it works out that if two secant segments share the same endpoint outside of a circle, then the product of the length of the one secant segment and its external segment equals the entire length of the other secant segment times its external. So what we're doing is we have these two secant segments, and we're taking the whole line times the part outside is equal to the other entire line times the part outside. Whole line times outside, whole line times outside are going to be equal. So when we look at this here, we're again dealing with products. So if we look at one of our lines, let's say RQ, the external length is what? 9. Now what are we going to multiply it by? It is the entire line, yes? So the entire line would be the exterior plus the interior. I need to move this down. Because the theorem stated that we had the exterior part of the secant line times the secant line itself. So the secant line itself for RQ is going to be 9 plus 11. It's the whole line. Now our other line, the exterior is 10. The whole line would be 10 plus x, because we have to add those two together. Now we really didn't have to write out 9 plus 11, because we know what 9 plus 11 is, and it is 20. So any questions on what we've done so far? Now at this point here we can do 9 times 20, which is 180, is equal to, well, we do have to distribute, and 10 times 10 would be 100 plus 10x, because 10 times 10 would give us 100, and 10 times x is 10x. We would minus 100 from both sides, yes. And if we minus 100 from both sides, well, these, well, in my back pocket, those would cancel. 180 minus 100 would be 80 is equal to, so we would divide both sides by 10. Let's do it in a different color. Divide both sides by 10, which would tell us x is equal to, and on this one here, they're just asking us to find the value of x. No, they're not. Or yes, they are. Because value of x, correct?
Yes.
Mm-hmm. And so we are done, since it's just wanting us to find the value of x. Any questions on any of this here? Any questions on anything we've done so far? Okay. So let's look at another one here. So here we're given external length of 3, internal length of 9, and an external length of 4 and an internal length of x. Exactly, so we would say 3 times 12, because the entire length would be 9 plus 3, and 9 plus 3 is 12, is equal to 4 times 4 plus x. We have to rewrite that out because we can't add 4 and x together. They're not like terms, so we can just write it as 4 plus x or x plus 4. Either one would work. So we can do 3 times 12, which would be 'cause we multiply through and we would get 16 plus 4x. And to get the 4x by itself, we would subtract 16 first. And our 16 minus 16 would cancel, leaving 4x by itself. So when we do the subtraction here, 36 minus 16 would give us 20. And last but not least, we would by 4. We divide both sides by 4, telling us x is equal to 5. Any questions on any of this here? Any questions on anything we've done so far? I feel like we're good with this here. We feel comfortable with this setup. Yes. Mm-hmm.
So you multiply the 9 and the 6 and set that equal to 5 times x.
So the theorem that we have for this here, let me back up, is based off of this here. If I'm given two secant segments, if two secant segments share the same endpoint outside a circle, then the product of the length of one secant segment and its external is equal to the product of the length of the other secant line and its external. So the two secant lines products of the whole line and the part outside is equal to the whole line times the part outside. So when we set both of these up, so 9 is outside times the whole line, 9 plus 11, is equal to 10, the part outside, times 10 plus x. Is how we go about that here. And the same for this here, so it'd be 3 times 9 plus 3, which would be 12. And then the other one would be 4 times 4 plus x. Does that kind of make sense for those here? So this one here, I think we feel comfortable with, but we'll do this one here because, again, we've got a few more variables. It looks a little different. But the overall process is not going to change, and we're still just finding the value of x. So one of our secant lines, the exterior is what? 3 times, well, the whole line would be what? 3 plus x minus 2. So even though I have an x minus 2, it's still we're adding those two segments together. One links x minus 2, the other is 3. We're just going to add them. Now our other line is going to be 2 is the outside. And the whole line would be 2 plus x plus 1. So any questions on how we got any of this here? Okay, well, before we go multiplying anything together, inside of both of these sets of parentheses here, there are like terms, yes? Well, x doesn't have any like terms, but 3 minus 2 would be plus 1. Plus 3 minus 2 is a positive 1. Equals 2 times, well, x doesn't have any like terms, but 2 plus 1 gives us 3. Any questions on this here so far? Okay. Now we can use the distributive property and multiply through. Our 3 times x would be 3x. Our 3 times 1 would be plus 3 is equal to, well, 2 times x is 2x. 2 times 3 would be plus 6. What can we do next? Subtract what? 2x? Yeah, 2x. Subtract 2x from both sides. Yes. I was making sure because there's several things we could subtract. Now the 2x minus 2x would be 0. 3x minus 2x would just give us x. And we'd have x plus 3 is equal to 6. And now we would be 3 from both sides, which would tell us x is equal to 3. And that's it. Now, because it didn't ask us to find any links, we don't have to plug it back in. So it's just asking us to find the value of x. Any questions on any of this here? But that's it. That's all we have to do for these here. Now, we could have made them, they could have made them a little bit harder, a little more challenging, adding in, instead of having the variables inside the circle, having them outside, can make the problems a little bit harder. Because then we're dealing with x squared terms and actually having to solve quadratics. So really making these harder, it's not going to make them harder, it's just making the solving more steps. You're going to have to do more steps in solving. And we'd have to go back to our quadratics and use them to be able to solve. Okay, the last theorem that we have is secants of segments and tangents. Now, if we're given a tangent line and a secant line, share an endpoint outside a circle, then the product of the length of the secant and its external, what we were just doing, is equal to the length of the tangent line squared. So whatever the length of the tangent line is, we're going to square it, and it's equal to the external times the whole secant line. So let's actually look at it, because it makes a little more sense when we look at them. Now this one here is not asking us to just find the value of x. It's asking us to find the length of RS. Well, the length of RS is just x. So once we find x, we find RS. So for this here, well, we know the external, well, the tangent length is 10, and it's going to be what? Squared is equal to, the external is x, and the whole line would be x plus 15. So this here is one of the ones that it's going to be a little bit harder. There's more steps involved. So any questions on how we set this up? Okay. Well, we can do 10 squared, and 10 squared is 100. Now at this point here, we can distribute our x, and x times x would be, and x times 15 is going to be plus. Now if you notice at this point here, we don't have x squared on both sides, like we did on the first problems. Because if we had an x squared on both sides, they would cancel out, like we saw before, and it'd make things a little bit easier to work with. But here, what we're going to do is we're going to subtract 100 from both sides, because these will cancel out, giving us 0 is equal to x squared plus 15x minus 100. Because whenever we have quadratics, second degree polynomials, we have a variable with a square, x squared, term, we want to get everything on the same side of the equal sign. We want to get it, we want to have this equation equal to 0. Because at this point here, there's two routes that we can go. One of them is factoring this, rewriting it as two sets of parentheses being multiplied together. Because if I have two things multiplied together to equal 0, one of them has to be 0. The other method is the quadratic formula. And we'll go that route this time. Because I have a feeling this formula here is somewhat familiar. Y'all seen this before? What? Because all this does is it corresponds to A, B, and C are the numbers in front of x squared, x, and the constant term. So, when we look at this here, and this formula, we're going to plug in B first. Well, what is the value of B? 15. So I would have negative B, so negative 15. Inside here, we're going to have 15 squared minus 4. Now A, because that's the next letter we come across, well, A is the number in front of x squared. Well, what is the number in front of x squared? 1. Number in front of x squared, well, there's not 1 written, so it's understood to be 1. And C is negative 100. And we take the signs with them, but it worked out that A and B, 1 and 15, were both positive, so we just took them as positive numbers. So any questions on how we plugged any of this in and utilize this formula here? So we plugged A in, so the two spots where there were A, since A is 1, we plugged 1 in. Since B is positive 15, so at the negative B we plugged in 15, which made us negative 15. And then for B squared, we plugged it in, so we get 15 squared. Now at this point here, we're just going to start calculating things. So when we look at this here, the first thing we can do is really everything with this square root, because all the ones that we'll do in here, you can type that whole thing in. And go on and type that into the calculator if you have it, because we can hit the square root of 15 squared minus 4 times 1 times negative 100. So we can type that all into the calculator. And if we type this all into the calculator, we get I believe it should be 25 once you type all that in. So once you type the square root in parentheses 15 squared minus 4 times 1 times negative 100 should get you 25. Well, we're not doing the plus or minus yet, because the 100 is Yeah, so we're just typing in the radical, the square root of 15 squared minus 4 times negative 100. So we just want to type that part into the calculator. Yeah, so we don't want to do the whole thing quite yet. But it should give us 25 if we type it in. Now the bottom part is 2 times 1, which would give us 2. Now, plus and minus, what this is really saying is that we have the positive and negative case. So we have negative 15 plus 25 over 2. And we'd also have that x is equal to negative 15 minus 25 over 2. Because plus or minus, positive or negative, is what that is saying. And at this point here, we can simplify these down. Because negative 15 plus 25 would be 10. And 10 divided by 2 would be 5. In our other case, we'd have negative 15 minus 25, and negative 15 minus 25 would give us negative 40. And if we take negative 40 divided by 2, would give us negative 20. This is number, I have to look and see. Example 3, use segments and secants, segments of secants and tangents. Now, since we're finding RS, well, we know any distance cannot be negative, so our only answer for this is x is equal to 5. X is equal to 5. All right, guys, you can go if you want to take your pictures. So for those that were in here for the whole thing, are there any questions on this here? Any questions on any of this here so far? Okay. And looking at the time that we have left, this is where we're going to stop for today. We'll finish this lesson, these note sheets up on Monday. We'll finish this up on Monday.